Hi, my name is Holly May Lewis and I'm a PhD student supervised by Professor Roger Webb and Professor Melanie Bailey. I've been optimising a spatially resolved extraction technique called direct analyte-probed nanoextraction, also known as DAPNe, which I've combined with liquid chromatography to analyse discrete areas of a sample. This presentation discusses how the technique can be combined with IBA to gain both elemental and molecular information. Obtaining a detailed molecular analysis from a discrete area of a tissue sample is important in many fields of biomedicine. DAPNe is a surface sampling technique which uses a nanocapillary driven by a nanomanipulator and is combined with mass spectrometry. Due to the 1 micron tip diameter, DAPNe has the ability to gain superior spatial resolution to other surface sampling techniques and can gain extraction spot diameters of around 100 micron. However, with DAPNe-MS, only molecular information is given, not elemental information. However, when combined with IBA, an area of interest can be located on an elemental map. This area can then be relocated using DAPNe, and a mass spectrum of the molecular chemistry can be acquired. So how does DAPNe work? The area of interest from the ion beam image is relocated using a microscope. A capillary tip containing an extraction solvent optimized for the sample being analysed is inserted into an ion manipulator. The tip is lowered in small increments until just above the sample surface. The solvent is injected onto the surface in a discrete area using a pressure injector. The solvent dwells on the surface and analytes are dissolved, which leaves an extraction area which can be measured using the microscope software. A back pressure is applied, causing the solvent containing dissolved analytes to be aspirated back into the capillary tip. The contents of the tip are then injected into a liquid chromatography vial, and the analytes are analysed using liquid chromatography mass spectrometry. To show how IBA and DAPNe LC-MS can be combined, a tuberculosis granuloma tissue section was analysed. The granuloma was first analysed using ion beam imaging to determine the elemental composition. There were 3 main areas of the granuloma: the necrotic region, the cellular rim surrounding the necrotic area, and then the surrounding healthy tissue. It was shown that elements such as iron and bromine had higher intensities in certain areas more than others. 12 different areas were then probed using DAPNe in each of the areas of interest. The approximate spot areas are shown in the microscope image. Each extraction was then analysed using LC-MS. Due to the high intensity of phosphorus shown on the IBA image, this could suggest high levels of phospholipids in the tissue. A lipid-specific chromatography method was used to determine which lipids were present in each area. The extracted lipids were separated according to their retention time and mass discharge ratio. A software called Lipid Search allowed the detected lipids to be identified, and the different areas of the granuloma were separated using PLSDA. The analysis gave a list of lipids that contributed most to the model and were most different between the areas of the tissue. The animal from which this granuloma was taken had also been dosed with a TB drug called bedaquiline, which contains a bromine ion. It was theorised that this was producing the BR signal in the IBA image. The bedaquiline peak area from the chromatogram was normalised to the DAPNe extraction area. No bedaquiline was detected in the necrotic region or the iron-rich region surrounding the necrotic region. However, it was detected in the bromine-intense region and the healthy tissue. When averaged across each area, it can be seen that the intensity was higher in the bromine region, which suggests this is the reason for the high bromine signal. To conclude, DAPNe LC-MS can be successfully used alongside IBA to determine the elemental and molecular composition of discrete areas of a tissue sample. DAPNe can effectively probe areas with a high intensity of an element to determine the molecular significance of this area compared to the surrounding areas. The addition of an LC separation step means different lipids can be distinguished between, even those with the same mass. Thank you for listening to my presentation. If you have any further questions, please do not hesitate to contact me. Thank you.